Okay. Let's see. Is there any comments on general on sets 4 or 5? Again, for reading questions, to see if you're ever actually looking at either one of the resources, either the notes that I put out that are on the site, or alternatively you can use a textbook. You can find it there too. But I see signs that that's still not being done. So what I've noticed is that there's a tendency for on the part of a lot of students to rely exclusively on what happens here during these 50 minutes or 75 minutes from whatever class you're in. When I was a student, I knew I needed to use whatever resources were available to me, all of them, whether it's from in class, textbook, seeing a professor at office hours, a lost art these days, things like that. Whatever it takes to get the information that you need. Set 4, for most part, went pretty well. One subtlety, and really only made a difference of a point, on problem 7, the one that went on about semi-stable solutions, and the last part asks you to actually solve the given DE, which most of you did. But then it asks for something else. Use that to confirm the behavior from the previous parts. And I'm going to be checking to see if you actually answered the question that was asked. And not many did. It turns out that although the solution formula that you come up with applies, regardless of whether the initial value y0 is less than 1 or greater than 1, because 1 is the equilibrium, in one of those cases, the solution actually blows up because the denominator becomes 0. So that's important behavior to be aware of. Now, as for problem set 5, again, reading question 1, a lot of people were answering an entirely different question. What I asked for was, where does the condition come from? Why is that? Basically, in other words, why is that the condition that's needed? If you're not sure what the question is asking, you can always ask. That's how these things are supposed to work. That it's better to choose the path of being more communicative rather than less, and simply going off assumptions that might be flawed. But you got to read the question more carefully. I see so many instances of not doing that. And one of the things that I try to strive for is to nudge you in the direction of thinking more carefully about these things. It's almost like everything that's happened up to this point has programmed you in a way, or conditioned you to act on reflex. And that's not a recipe for success. You have to be able to adapt to unfamiliar situations as they come up. Okay, let's see. I think the textbook problems, for the most part, went pretty well there. I know a number of careless mistakes, but so you have to be careful about those, especially when it comes time for a test. Now, hopefully, and I want to bring this point up again too, and I do send the occasional email announcement. I get a sense that in some cases those are being missed. You are responsible for keeping on top of your USM email, which is what I use to send any announcements. So if you have been on top of that, you'll know that there's a little bonus opportunity coming up today. So I'm speaking at the weekly seminar. It's at 2 o'clock right across the hall. If you can attend, you will get the bonus points. If you are truly unable to attend, I will provide an alternative. So what I'll be doing is, just as I'm recording this and all the lectures, I'll be recording that as well. So if you really can't, so it'll be easier for you if you can attend. If you can't, let me know, and I'll give you some other way based on the recording. To also, so what I would do is add 10 points to your test 1 grade. So, okay. Okay, so hopefully I'll see at least some of you there. Okay.
How long do they last?
Oh, it's generally 50 minutes.
How many?
50.
50.
Yeah. Okay. All right.
You said it's at 2 o'clock, right?
Yes. Yeah. Okay. Now, because I end up falling a little bit behind, and I'm going to hopefully do some catching up either today or Monday. The due dates for homework sets are deliberately out of order. So it's an unusual effect of problem set 8, which is based on what Dr. Tian covered in class on Wednesday. Is what? I didn't save a section yet. Problem set 8, which is on section 3.3. That's actually going to be due before problem 7 because the previous section 3.2 I didn't fully cover last Friday, and I plan to finish that today. One reminder about the homeworks. It'll be. I'd appreciate it if you write on your assignment which problem set it is. Problem set 1, 2, 3, etc. I mean, if you write the section, yeah, I can figure it out. But just for convenience, please write the problem set number that you're doing. It's the one that's on the handout. Okay, but hopefully only a few meaningless seconds were missed. Okay. Now, does anyone have any questions about problem set 6, which is on section 3.1? All right, so that was all perfectly easy for you. Oh, yes. 15. Okay, so all 5 textbook problems are of the same form where you're solving something of this form for some constants p and q, and okay, now we have some initial conditions. Well, the first 2 problems don't have this, but the rest of them do. Now let me ask you this. The situation where you went ahead and worked it out, and then you checked against the answer and it didn't match? Okay. I have a hunch as to why. So the thing to keep in mind is most of the time, the initial time that's used, we just use 0. So what happens is you have your characteristic equation, quadratic equation, r squared plus pr plus q is equal to 0, which gives you roots r1 and r2, which in this section will be 2 distinct real numbers. And then you have your general solution. Y of t is constant, e to the r1t plus another constant, e to the r2t. And when you're given initial conditions, like in this problem, the system you're supposed to solve is, so if I refer to this as y1 of t, and I call this y2 of t, then you solve this system of equations. You plug in the initial time, so that'd be c1 e to the r1 t naught plus c2 e to the r2 t naught, and that must equal the given value for the initial condition. And then for the derivative, well, in this case, the derivative just is easy to compute because they're exponentials. So you end up just multiplying them by the corresponding R values. Okay, and generally in examples, I just assume that the initial time is 0. So you get a system like this: C1 plus C2 equals Y naught, and then R1 C1 plus R2 C2 is Z naught. So T naught equals 0 just reduces to that case. But in this problem, it's a little different. The initial time is 1. So if you went through the process and didn't get the right answer, chances are it's because of that. Okay. So you're always plugging in whatever the given initial time is, and then for first equation, second equation, go ahead and compute a derivative, then plug in the initial time into that. Okay. Okay. Now, any other problem set 6 questions?
On 9 and 15, it asks us to sketch a graph of.
Right. So the things to watch out for. Better make sure I'm getting this. Okay. For a behavior of a solution, and particularly interested in the cases t just keeps increasing off to infinity. Okay. It depends on whether your roots of your characteristic equation, R1, R2, are positive or negative. So if you have R1 positive, that is exponential growth. Or this is for any of the values, R1 or R2, it doesn't matter. If they are negative, then you have exponential decay. Now, and then the constants that you get, your C1 and C2, I suppose it's exponential growth, will determine if it's growth towards plus infinity or towards minus infinity. If you have a situation where one of these values is positive and the other is negative, then the part that's exponential decay, you might as well not even include that because it's so insignificant compared to the exponential growth. So really just this very brief understanding is all I'm looking for. Exponential growth versus decay. Now, okay, well, one other situation, if something equals 0, then that part of the solution is a constant because you get e to the 0, which is 1. So if you have a situation where one of the roots is 0 and the other is negative, you get a solution that quickly becomes like almost constant. So that's the other interesting case. So growth, decay, or staying stationary. Every question? Now I'm having a flashback to when I would teach pre-calculus and show the graphs of different kinds of exponential functions. I go, here it grows, here it decays. So all those things come into play here. Okay. Okay. Now, continuing with section 3.2. Okay. And just what I add, just because I always like to toot my research students' horns. As you know, I was at a conference all week in Atlanta, and the main purpose was so that several of my research students, turned out to be 5 of them, were all to give presentations. So they're either getting up in front of an audience of experts in the field, so more senior people, and giving a 15-minute presentation, or doing up a poster and being at that poster for a couple hours, for anyone to come by and also ask questions. And I have to say, they did an amazing job. Certainly, when they're just still the students and in front of and surrounded by 1,500 or so professors or industry researchers and so forth, it can be a very terrifying experience. But they didn't let that stop them, and everything went very well for them. So. And that's when good things happen when you. As students, I remember what it was like. That you're very afraid and insecure about a lot of things, and that's fine. Everybody is, no matter how well they hide it. But you don't let it stop you from doing the things you need to do. Okay. So, continuing 3.2. First, maybe the Wronskian. I have a general second-order linear differential equation where now the coefficients P and Q, we're most interested in the case where P and Q are constants, but now and then we'll do cases where they're not. It's equal to 0, which is expressed as, differential operator L of y is equal to 0, where that notation refers to, this is a differential operator. So that's just my shorthand for that kind of equation. And then we have the usual initial conditions imposed at a time t naught, whatever that might be. And to refresh your memory, the actual Wronskian, hold on. If I let y1 of t, y2 of t be two solutions of a differential equation. So at this point, I'm not thinking about initial conditions yet. So for instance, in the problem over there, y1 could be e to the r1t. y2 would be e to the r2t. All right, so just any two solutions that at least satisfy the differential equation. And then recall that the Wronskian of y1 and y2 is written this way, and it is itself a function of t. So it is the determinant of y1 of t, y2 of t in the first row, and their derivatives, or first derivatives, in the second row, which is also written this way. It's using the absolute value signs. Okay. And how that works out is just y1, y2 prime minus y2, y1 prime. So notice the terms are subtracted. Each term has only one of the functions being differentiated. The other is left alone. And as far as when you have two solutions, which one is y1, which one is y2? For how we use this, it doesn't really matter, because if you swap y1 and y2, that would only change the sign of this. And what we really care about is this expression equal to 0 at a particular point? So, and there's some of the problems in this set 6, set 7. Just deal with your two solutions, compute the Wronskian. But I need to go over how we interpret the Wronskian. And here it's easy to compute because this is only a second order equation. If we had a higher order equation, like involving third derivative or fourth derivative, we'd have more solutions. We'd have a Wronskian, which would be a determinant of a larger matrix. And that's going to come back to haunt you in chapter 4, where we actually do solve these higher order equations. Okay. So what I'm going to do to try to present this a little more compactly is, and in fact, certain theoretical results are often stated this way. You have certain statements that are all equivalent to one another. In other words, if one of these is true, then all of them are true. So you can think of one as just saying the exact same thing as any of the other ones. So, first statement is, suppose the Wronskian of the two solutions at some given point t naught is non-zero. Okay. Then what that implies is there exist constants C1, C2 such that the solution of this initial value problem, the differential equation, which I'm again abbreviating as Ly equals 0, and then the initial conditions at the same time t naught, is given by that's what t. But there exist constants so that this is the solution of this initial value problem with these initial conditions. And in fact, I can go a little further. Okay. I could actually write down a formula for C1 and C2 in terms of expressions like the Wronskian itself, where it's like as a determinant. So C1 is, so it's a fraction. The denominator is Wronskian, evaluated at t naught. And then the numerator here is also a determinant, where for C1, I fill in y naught and z naught, the initial values, and then I have y2 of t naught and y2 prime of t naught. In other words, it's exactly the same matrix as you use for Wronskian itself, except because it's C1, the first column is replaced by your two initial values. And similar expression for C2. You have a Wronskian evaluated at t naught in the denominator, and in the numerator, you replace the second column with your initial values, and then you have the first column is exactly the same as what you use for the Wronskian. I should mention where this formula comes from is something that might have been covered in your linear algebra class. It's called Kramer's rule. So it gives you a way to formulaically write down the solution of a system of linear equations. Because what are you doing when you have initial conditions? You set up your two equations, like I wrote down on this board earlier, for C1 and C2, and you solve them. Well, that's the solution for whatever initial time and whatever initial values you have. Now, Kramer's rule is very impractical if you get to systems of more and more equations, like beyond 3 or 4. It's ungodly tedious. But for just system of 2 equations, pretty compact. In fact, the exercise we did a week ago, where I had you play around with certain equations and work out the initial conditions and try to come up with a general formula. This is that formula. It's just I'm making it a little more general because this is true regardless of whether the coefficients p and q are constant or not. last Friday you were dealing with a case where they were constant, but this works no matter what. When they're not constant, the challenge is actually getting y1 and y2 in the first place. Okay, so that's the second statement. The third statement is all solutions of this differential equation have this form, that they're a linear combination of y1 of t and y2 of t. You just had to find the constants needed to satisfy any initial conditions that you have. So I want to emphasize, all it takes is for a Wronskian to be non-zero at one point, and that is enough that all solutions have this form. Because what that says is the solutions y1 and y2 are not multiples of each other. They're linearly independent, so they describe any solution of this equation you could possibly have. Okay, so then some terminology. If this is the case, we say that this set of solutions, y1 and y2, we call them a fundamental set. Of solutions. Right. Because they can because they can be used to describe all the solutions. Infinitely many of them. Okay, so the other thing I wanted to cover. So this is one result about fundamental set solutions. Let's suppose that y1 of t, y2 of t. This relates to the exercise I had you do last Friday. So these are two solutions of your differential equation, y equals 0. That satisfy these initial conditions. So y1 at your initial time is equal to 1. The derivative is 0 at that time. And then the second one, y2, satisfies the opposite initial conditions. So the solution is 0 at the initial time, but its derivative is 1. So it should ring a bell that I had you solve a differential equations with constant coefficients with these exact initial conditions a week ago. So if this is the case, then it's guaranteed that y1 and y2 is a fundamental set of solutions of this differential equation. Okay. What else you can have is, well, okay, never mind that. But I'm not going to really do a full proof, but I'm just going to explain why that's true. It's because the Wronskian, in this case, at the point t naught, turns out to just be the determinant of this matrix, which if you were to work it out, would just be 1. So it's non-zero, which is what you really need. Can anyone tell me what that's called? Identity matrix. Abbreviated as a capital I. Okay, so in that case, would satisfy these, because your Wronskian at t naught come from these initial values at t naught. Okay. All right, and then one other item is that there actually is a fairly simple formula for the Wronskian, almost not complete. It specifies it up to a constant. So another theorem, and we'll make use of this later, because right now we've covered a case where your roots lambda 1 and lambda 2 are distinct. But what if they're equal? So this result is going to help us out with that, which I meant to cover on Monday, but that's going to wait. It's called Abel's theorem, which says that for this differential equation, Ly, with these coefficients, some function p of t y prime plus some other coefficient q of ty equals 0, the Wronskian of y1 and y2, now, there are infinitely many possibilities for y1 and y2. Because if you have any fundamental set of solutions, if you take linear combinations of them in a way that keeps them linearly dependent, as in they're not multiples of each other, that's another fundamental set of solutions. There are infinitely many fundamental sets of solutions. But they all have one thing in common. Bless you. That the Wronskian of all these fundamental set of solutions has the same form. It's some constant, so that's the only opportunity for variability here, exponential to minus the integral of p of t dt. Okay. Yeah. Which you've seen something like this before, where something like an integrating factor for a first order equation. And in fact, unfortunately, I don't have time in these last 5 minutes. Well, I could give a sketch of this. This is on page 43, where this is covered. And use these last 5 minutes to give you an idea as to why it always condenses to that, regardless of what y1 and y2 are. I hope those are not noises of packing up I hear. I do have 4 minutes left. Okay. Because what you can do is, I'll put proof in quotes because I won't have time to do the whole thing. So if you have like y1 double prime plus p y1 prime plus q y2, no, y1. But chatter here is kind of distracting. Can you please cut it down? Is equal to 0 because y1 is a solution. But what I can do, therefore, is I can multiply this by y2 on both sides. And then I can plug in y2 into the same equation and also get 0 and multiply that by y1. So if I take these two equations, so y1, y2 double prime plus etc. is equal to 0, and I subtract these two equations, then what I get after simplifying as much as I can is that y2, y1 double prime minus y1, y2 double prime plus p times y1 prime y2 minus
What's the dot, is that just?
repeat the same thing except with y2. Sorry, I'm having to rush, but it's all done out in the notes. Y1, y2 prime minus y2, y1 prime is all equal to 0. So if I take these two equations and subtract them, I get this. This right here, that actually is a Wronskian. Whereas this expression here, it's not obvious from this, but I work it out in the notes. This is actually the derivative with respect to t of the Wronskian. Because what would happen is, if you just wrote out the Wronskian, and it took the derivative, you get 4 terms because of a product rule, but 2 of them cancel out, and you're left with just these 2 terms. So now I have w prime, where w is a Wronskian, plus p of t w is equal to 0. So in other words, for Wronskian of y1 and y2, solutions of a second order equation, satisfies a first order differential equation. Because remember, Wronskian is a function of t also. So I can say Wronskian is some constant that's unknown, exponential because you know how to solve these first order equations. This is linear and separable. So we talked about this kind before, and that's how you solved it back then. So that's the idea. Okay. So on Monday, I'll cover something. So thanks for helping us stay on track.